Carbohydrate acetals are generally called glycosides. An acetal of glucose is called a glucoside. Acetals of mannose are mannosides. Acetals of fructose are fructosides. So this is the glucose. You are treating with methanol and HCl. Then you are getting methyl alpha D glucopyranoside and methyl beta D glucopyranoside. This is the glycosidic linkage. This one. Now, what is the mechanism of formation of glycoside? At first, this OH is taking a proton and it is being converted into a very good leaving group OH2 plus. So this oxygen is giving its electron here in this bond and this bond is being broken. So after the elimination of water, we are getting this kind of molecule, this one, where there is a double bond and oxygen is in the plus oxidation plus 1 state. Now this methanol will attack and it have two opportunities. It can attack either from the upside or from the downside. So if it attacks from the upside, then you will get this methyl beta D glucopyranoside, this one, because here OCH3 group is attaching at the upper position, that means in the equatorial. And if it attacks from the downside, then you will get this, and after the deprotonation you will get methyl alpha D glucopyranoside. Glycosides are stable in basic solutions because they are acetals. In acidic solutions, however, glycosides undergo hydrolysis to produce a sugar and an alcohol. The alcohol obtained by hydrolysis of a glycoside is known as aglycon. In acidic solution, glycosides show mutarotation. So this was your glycoside and you are just treating it with some acid. You are just giving a acidic medium. So this glycoside will be broken into a sugar and a alcohol. This alcohol is called aglycon. In case of salicin, this is the carbohydrate moiety up to this, and this one is the aglycon moiety. You should remember that this oxygen is of the oxygen of the alcohol, not of this sugar. Salicin is a compound found in the bark of willow trees. As early as the time of the ancient Greeks, preparations made from willow bark were used in relieving pain. Eventually, chemists isolated salicin from other plant materials and were able to show that it was responsible for the analgesic effect of the willow bark preparations. Salicin can be converted to salicylic acid, which in turn can be converted into the most widely used modern analgesic, aspirin. Now see the mechanism of the hydrolysis of a glycoside. So this is your methyl beta D glucopyranoside. So at first this oxygen will attack this proton, any one of these three, and then it will become a good leaving group CH3OH plus. So now this oxygen will donate its lone pair here and this bond will be broken. So you will get this structure, and after that water will come, and water can attack now from the upside or from the downside. So if it attacks from the upside, you will get this. When after deprotonation, you will get beta D glucopyranose. And if the water attacks from the downside here in this stage, then you will get this one, this compound, and after deprotonation you will get alpha D glucopyranols. In neutral or basic solutions, glycosides do not show mutarotation. However, if the solutions are made acidic, glycosides show mutarotation. Why? You have to explain this. The answer is because glycosides are acetals, they undergo hydrolysis in aqueous acid to form cyclic hemiacetals and then undergo mutarotation. Acetals are stable to base and therefore in basic solution they do not show mutarotation. Now this is the structure of salicin and this is the huge structure of doxorubicin. I don't know anything about these two. These are just only in the medicinal purpose. If you are interested, you can see further about these two. So I am just skipping this page.